Good day, everyone. Today I will be talking about transformers, which are the neural networks that underlie large language models and many of the AI tools that we use nowadays. So AI has attracted great attention by the general public in the last couple of years, mainly due to the emergence of large language models or LLMs. And there is a lot of buzz about AI. But it is quite interesting to see that most of the progress in these years is due to a rather simple idea in statistical learning, which is inner product attention. So in this talk, I would like to present this concept in a language that most of us can understand, starting from the intuition and gradually delving into the theoretical aspects. Hopefully, by understanding attention mechanisms, we obtain a tool that we can apply in many inference problems besides LLMs. So I will set the scene by talking a bit about LLMs and how chatbots generate text. Then we'll realize that these ideas can be applied to more general problems in statistical inference, and this will allow us to formalize attention in a very neat fashion. Then we'll get back to the application domain, where I will explain how we developed a radio map estimator using a transformer, and finally we'll get our boots in the mat. I will present an Android app that we developed and deployed in the real world, which implements the transformer here. So let me start by talking about LLMs. In particular, I will be briefly describing how a chatbot works. A chatbot takes a text provided by the user, right, the so-called prompt, and then it appends other text like previous prompts, previous outputs of the model, metadata about the user, things like that. And it gives the resulting text to a text generator, which produces more text. Okay, and then the chatbot shows that text to the user. So let's see how a text generator works. Text generator essentially takes as an input a sequence of words, performs some operations, and these operations result in the generation of the next word. So this word is then appended to the input, and the same operations are repeated. That will result in the next word. Okay, and then that is appended at the input again, and so on and so forth. So this process is repeated for each word generated at the output. Okay. So this way of operating is the reason why this is typically called, or it is said to be autoregressive, right? And for those with signal processing background, this is like an IIR filter or the generation of an AR process. And it is important to say here that in practice, this kind of algorithms don't work directly with words. They work with tokens. Tokens are subword units, so sequences of one or more characters. But conceptually, it is the same thinking in terms of words or thinking in terms of tokens. Okay? It remains to see what are the operations performed to produce the next token. And these operations are two. The first one produces the posterior probabilities of each possible next token, right? So, for example, if the given that the previous tokens were the black cat, the probability that the next token is its is given by this number. The probability that the next token is this number, and so on, as shown in this example. Some words may have a very low probability, right? For instance, this one would be like grammatically incorrect, right? So you cannot say the black cat are, yet the probability is not 0, because people may also make mistakes, or there may be typos and so on. This one, for instance, is a word that does not often go with cat, so that is like it also has a small probability, right? So there will be thousands of rows in this table, and the probabilities will add up to 1. Okay? So then a random number generator chooses one of the tokens according to these probabilities here. Okay? And that will give us the next token. So this is, as I said, repeated many times. So when does the process end? Well, it ends when so there is a special token called the end token. Okay, so the process ends when the random number generator chooses this end token. Okay, so this is when like ChatGPT finishes the answer. Okay. So the core of this of a text generator is essentially this block here, which produces the posterior probabilities, and this is precisely the LLM, right? And nowadays LLMs are implemented using transformers, which are deep neural networks that use an attention mechanism. Not to be confused with the toy or cartoons that those of us that grew up in the 80s or 90s are familiar with. So let's now try to understand the intuition behind the attention mechanisms used in transformers. And to this end, it is very instructive to think of how attention works in natural language. So in natural language, we produce sequences of words. Each word has quite specific meaning, but arranging the words together, forming sentences, we create more complex meanings, right? It's like it's as if words interact with each other and exchange information, right? And we typically think of two different classes of interactions, those essentially dictated by syntax, and those determined by the meaning of the words. So, for example, here in this sentence, the house is white. We know by the syntax that white refers to house, right? However, if we think of this other sentence, the car near the house is white. Well, here we have exactly the same sequence of words as here, but by semantics we know that white refers to car. Okay, and there are other the other class of interactions are those based on the meaning, right? So, for instance, if we say the cat ate the food because it was hungry, we know that hungry, this adjective, refers to the word cat, right? However, if we say the cat ate the food because it was warm, right, we will conclude that this adjective refers to food, right, despite the fact that both sentences have exactly the same syntax, right? We are just looking at the meaning. In fact, this kind of subtlety was something language models really struggled with until recently, right? So traditionally, Google Translate had trouble to distinguish these two situations, which is even more manifest in other languages where pronouns have like gender, and there's other languages like French or Spanish may see these issues to a greater extent. So to sum up is we see that it's like if each word pays attention to different words to different extents, right? And we also can say that or think that each word enriches the meaning of the related words. And this is sort of the notion of attention that is exploited in transformers. So now that we understand the intuition behind attention, let's try to understand it from a mathematical way, okay? And to this end, let's look at several problems that can be tackled using the same attention ideas, okay? The first problem is, not surprisingly, the one that we have seen so far. So given a sequence of tokens, the problem is to obtain a vector with the posterior probability of the next token, right? So the dimension of this vector is precisely the number of possible tokens, right? So the tokens are in a finite dictionary, right? And since the tokens are incidentally represented by vectors in transformers and this kind of algorithms, what we have here is a problem where the input is a collection of vectors and the output is a vector. So there are other problems that are of a similar form. For example, the problem of time series forecasting, where the goal is to predict the next vector in a sequence. Okay. And another related problem is function estimation. Consider, for simplicity, a real valued function. And suppose that we are given n observations, which comprise an observation point xn and a noisy observation of the function at the point xn. Okay. So given these observations and given an evaluation point x, right, the problem is to estimate the function at this evaluation point x. Okay. So as you can see, these problems bear quite a bit in common, at least from an abstract perspective. And it is important to note, as we will see, that the number of inputs in these problems is arbitrary. Okay. So many people focus on the first problem when they think of a transformer, but I find it much more insightful to look at the function estimation problem when it comes to understand attention. So let us delve a little bit deeper into this problem. Suppose that we are given some observations and we need to estimate the value of the function at this point. How can we proceed, right? So one very simple approach would be to just take a weighted average of the observations, right? And it is not surprising that many famous estimators are precisely of this form. So, for example, in k nearest neighbors, we would assign a weight of 1 or a constant to those observations that are among the k closest observations to the evaluation point, and 0 to the others. Another famous estimator would be radius nearest neighbors. In this case, we assign a weight of 1 to those observations that lay within a radius r from the evaluation point. And it is important to note that this one here can be written as just a function of xn and x. And this is actually a property shared by many other estimators. So for instance, this Shepard's method, right, this assigns a greater weight to those observations that are close to the or closer to the evaluation point, right? And also these kernel estimators, where this alpha, these weights alpha n are obtained by evaluating a kernel function, right? So this alpha n's, we say that, or we can see that this alpha n quantifies how relevant the nth observation is to estimate the function at the evaluation point x. And this is why these alpha n's are referred to as attention weights. So now we have arrived at the most important slide of this presentation. This is the real deal. This is the fundamental reason behind the progress in AI in the last few years. I am talking about inner product attention, which prescribes that the attention weights are given by the exponential of the inner product between these two vectors. So let's see this with a picture. Here we have that the input vectors are xn and x as before, and these vectors are mapped into a vector space by means of these two functions k and q. And here in this vector space, similarity is quantified by the inner product. So remember that the inner product is essentially a correlation. It's a decreasing function of the angle between vectors. So it is commonly used as a way of quantifying similarity. Okay. And then the exponential is taken to ensure that the weights are positive. Okay? So this vector k of xn is typically referred to as a key. And we can think that it encodes the information that xn offers, right? So it is like a vector that tells us what xn knows about, right? It's like it tells us the topics where xn has knowledge, let's say, right? This is like the intuition. And then q of x is a vector typically referred to as a query, right? It's like a question, right? We can think of it as encoding the information that x is interested in, what it wants to know about, okay? And these two functions are learnable, right? So they must be trained so that they implement the notion of attention that is most suitable to specific to the problem at hand. It is also instructive to recognize a softmax operation that is implicit in this way of setting the attention weights. So let us remember the expression for our estimator, and let us absorb this denominator into the attention coefficients, right? If we do so, we will, and we substitute this expression, then we will arrive at this equality here, where we can recognize that due to this exponential, if one of these terms dominates over the others, is significantly greater than the others, then the corresponding attention weight will be close to 1, whereas the rest of the attention weights will be close to 0. And this resonates very well with the notion of attention in our brains, right? So when we pay attention to something, we focus on the relevant things, and we tend to suppress the rest of the information. So now let me introduce an operator that will allow us to construct a transformer using more basic building blocks. Okay, So the attention operator takes a set of reference vectors which play the role of the observations in the function estimation problem that we saw, right? But this is applicable much more generally, right? And it also takes as an input a vector x. And it returns another vector, which is obtained with the weighted average that we saw earlier. The difference with what we saw before is that here we had y's. Now we have more general term. This is v of zn, right? This is the result of evaluating the function v at the point, the reference point zn, right? And this is this vector v of zn is typically called a value, right? We can the intuition here is like the information that or that it encodes the information that zn carries, right? This function v is learnable as the other two, and it generalizes the y, right? So the information in the case of the function estimation problem, the y's are part of the nth observation, right? So it's clear, right? Although I will explain this more into detail later. And the value function is used because this allows composition, right? So we can stack attention operators one on top of each other. The attention weights are the ones that we saw earlier, but we typically write here normalization constant that facilitates learning. So the intuition here is that this is, we can think of this as a function of x, right, that returns another vector with information that it that is brought from this like side information or set of reference vectors, right? So this is like words exchanging meaning as we saw earlier, okay? And these three functions in total, key, query, and value, are typically linear. So the trainable parameters that we have in an attention operator are these three matrices here. And this is a graphical depiction of the attention operator. Note that we have one key vector and one value vector per reference vector. However, we have a single query vector, okay? And this is a justification of my earlier claim that the attention operator generalizes the function estimator that we saw earlier, right? So indeed, one can note that both these terms will coincide if one sets the reference vectors to stack the observation values and the observation points, and setting the value function to select the observation value from the reference vector, right? Selecting the first entry, right? And this estimator can be certainly applied to the function estimation problem, but it may have some limitations. So remarkably, this estimator will not be invariant to translations, right? So this means that if we change the coordinate system, the estimate will generally change, right? So it is desirable in many problems to ensure invariance to translations, right? And fortunately, it is easy to achieve this here if we just subtract the evaluation point from the observation point. Okay. This is like shifting the or moving the coordinate system to the evaluation point, right? So it is as if we always we shift the observations in such a way that we always have to estimate the function at the origin, right? And it is also possible to introduce or make this estimator invariant to rotations using a trick that we will see later. So now, just for completeness, let's see how one would train an attention operator to solve this function estimation problem. This is just to get some more insight. Suppose that we are given a data set with j realizations, right? So it's like we have one set of n plus 1 observations per realization of the function f, right? One can construct a very simple mean square error loss by, for instance, choosing the first observation in each realization as the target and trying to estimate it using the remaining observations, right? If we do that, then we arrive at this expression here. This is the quadratic error, right? This is the target, and this is the estimate. Okay. And of course, multiple targets per realization are also possible, although the notation gets more complicated, so I will not write the expression here. Training then means finding a local optimum of this function here, right, with respect to the trainable parameters, which remember are the three matrices in the query, key, and value functions. And this is an example of estimation using the this attention operator with this translation invariance modification that I described. So here the true function is sinusoid, and the observations are these dots here. We see in green the 4 nearest neighbors estimator, right? It's a KNN with k equals 4. And in red we see our attention operator. Okay, so of course this can still be improved, and that's why we are going to get more complicated structures from the attention operator. In particular, let me define a few more operators, which are essentially the Lego blocks that we will be using to construct transformers. The first one is cross-attention head. A cross-attention head is the result of applying the attention operator to each column of a matrix. Okay, so we have m vectors at the input and m vectors at the output. Okay. So note that the order of this second argument matters. That's why we are using a matrix here. However, the order of the reference vectors doesn't matter. That's why we use a set, right? Remember that in mathematics, a set is a collection of elements where we don't assign any order to those elements. Okay. And then we have the so-called self-attention head, which is like a cross-attention head, but the reference vectors are precisely the columns of x. Okay, so again we take the input comprises m vectors, and it also returns m vectors. And then we have the so-called causal self-attention head, which is like a self-attention head, but the mth column of the output depends only on the m first m columns of the input, right? So in other words, the 7th column of the output does not depend on the 8th, 9th, 10th, and so on columns of the input. Okay. So now that we know what an attention head is, we can construct what is referred to as an attention block. An attention block is essentially an attention head with more elements around. So we typically have layer normalization steps. We typically have residual connections. This is very, very important. And we typically have multi-layer perceptron. Often with one hidden layer. Okay, so here it is important to realize that all these operations, other than the attention head, operate separately for each of the input vectors, right? So here we put m vectors at the input, and each of the only part where information goes from some vectors to the others is here in the attention head, right? So this is like the point where the words give meaning to the other words. Okay. And stacking attention blocks, and perhaps including also some linear layers, we make a transformer, right? And my last slide of this part is about multi-head attention. This is also a very common term. Here what we do is to take the input vectors. Here we have like 4 input vectors. We slice them along the rows, and each of this group of rows is sent through a separate attention head. And finally all the obtained vectors are stacked with each other, right? So it's like multiple attention heads and running in parallel. And this is a common technique, but it does not necessarily help, right? So it only helps sometimes, and it is not fully clear when it is helpful and when it is not. We oftentimes need to try and see what is the best number of heads. It can be 1 or it can be more than 1. All right, so now that we understand the intuition and the math behind attention, we are ready to solve real-world problems using transformers. In particular, I will be now briefly explaining a radio map estimator that we presented 2-3 weeks ago at ICC in Montreal. So let me start by providing some background information about the problem that we address in this paper. The paper is about radio maps. So what is a radio map? A radio map is essentially a function that provides the value of a certain communication metric for each spatial location, right? So for instance, this map here provides the power that a communication terminal, like a phone, would receive it if placed at each of these spatial locations, right? So this map essentially would tell us how good the connectivity of our phone would be, right? So the more power, the better, right? But one can construct a radio map for any other relevant metric, right? Such as interference power, PSD, or things like that. This figure is an example of a real-world radio map that we constructed with measurements that we collected with an autonomous unmanned aerial vehicle. And radio maps find a great number of applications because they allow us to know the quality of the connection at a given point before we actually go there, right? So this is, for instance, relevant if we need to plan the trajectory of an autonomous vehicle that needs to be connected to the network. But it is also relevant in many applications in the communication domain, right? So it's useful, for instance, for cellular operators to manage their networks, identify low coverage spots, manage or set many of the parameters in their configuration and so on. So now I will be briefly presenting the main contributions of the paper that I mentioned earlier. The first contribution addresses the radio map estimation problem, where the goal is to construct a radio map using measurements distributed across the area of interest. Here we developed an estimator using a transformer. And the second contribution deals with active sensing for the radio map estimation problem. So here the goal is to decide precisely where to collect these measurements to maximize performance. And we achieve or we do that by extending the transformer from this first contribution. So let us start by formulating the radial map estimation problem. This problem is nothing but the function estimation problem that we saw earlier with different terminology and notation. So, for example, instead of talking about observations, we typically use the term measurements, okay? And instead of saying observation points, we typically say measurement location. The observation values are therefore referred to as measurement values, and again comprise a signal term, right, which is the result of evaluating the true function that we would like to estimate at this measurement location, and also noise. So given these measurements and target location, the problem is to estimate the value of this function at this target location. So I don't really want to spend much time discussing the literature in detail. It is easier if I explain the main point by means of a figure. So the main idea is that all existing estimators for this problem that can learn from data rely on grid discretization, right? So that essentially means that they construct a 2D or 3D grid in the region of interest, and they assign each measurement to the nearest grid point, right? After that, they construct a matrix or a tensor where each entry is set to the average of the measurement values assigned to the corresponding grid point, right? So there will be some grid points to which no measurement is assigned, and that will result in the corresponding entry of the matrix or tensor being empty. So what these algorithms do is to fill those missing entries, right? These existing deep learning estimators for this problem are essentially matrix completion or tensor completion algorithms. Unfortunately, relying on a grid entails serious disadvantages. One of the most obvious disadvantages is the limited spatial resolution. So note that the spatial resolution is determined by the grid spacing, which is the distance between adjacent grid points. And the achieving a high spatial resolution requires a small grid spacing, but this will in turn require potentially very large number of grid points, right? So think, for example, of a 3D grid. There, if we decrease the grid point spacing by a factor of 2, then the number of grid points will increase by a factor of 8, right? And that will eventually result in a significant increase in computational complexity. So in other words, with grid-based approaches, the spatial resolution that we can achieve is limited by the available computational resources. Another disadvantage of grid-based approaches is the lack of translation and rotation equivariance. This is because a small change in the grid will result in a change in the assignment of measurements to grid points, and that will change the estimate, right? So that makes little sense in many problems. For instance, in radial map estimation, where Maxwell equations suggest that estimates should be invariant to translations and rotations. Note also that I'm talking about equivariance sometimes, other times I say invariance. This is just a mathematical distinction. Sometimes we think of estimating the map at a single point, other times we think of estimating the map as a whole. So depending on the case that we consider, we talk about equivariance or invariance, but both of the terms refer to the same idea. And existing deep learning estimators suffer from other disadvantages, not because they use grid discretization, but because of their design. So, for example, they estimate the map at all the grid points, even though estimates may be required only at a subset of grid points. And also, they fail to accommodate measurements outside the mapping region, right? The main idea in this paper is not to formulate radial map estimation as a matrix completion problem. Instead, we formulate it as a function estimation problem, and then we apply the ideas in the first part of the talk to come up with the first gridless estimator based on deep learning. As a result, it will naturally overcome all these limitations. So let me briefly explain the design of the proposed estimator. We would like it to satisfy several properties. Specifically, we would like that its spatial resolution is not limited. We want it to be invariant to permutations of the measurements, invariant to translation, and invariant to rotation. And we would like it to accommodate any number of measurements, even outside the mapping region. So the key idea is, as I mentioned, to apply a transformer for the function estimation problem. By doing so, and by properly designing the input features, we will be able to satisfy these properties here. So let me explain what we do with each measurement. We first apply the trick that we discussed earlier, where the evaluation point is subtracted from the measurement locations to ensure translation invariance. We also apply the same rotation to all measurements. This is kind of a normalization that introduces invariance to rotation. And then we also add the polar and Cartesian coordinates of the normalized measurement locations, and this is a way of complementing this information with cooked pieces of information that the transformer does not need to learn. We are essentially facilitating its understanding of the measurements, right? And by obtaining this vector for each and every measurement, we can form this matrix here, which we pass to a transformer. The transformer has a linear input layer, and the attention blocks are causal, right? I will explain why in a second. The output is a vector whose length is precisely the number of columns here, which is the number of measurements. The reason why we use causal attention blocks is because we don't want to train the transformer for estimating a map using one measurement, then train the transformer to estimate the map using two measurements, then three measurements, and so on. We would like it to learn how to estimate a map given any number of measurements. So by using a causal attention block, remember the mth output here will be a function of only the first m columns, and that means that we can train this entry to be the estimate of the map at the evaluation point given the first m measurements, right? So in other words, we can, if we are given a data set of this form where we have j realizations, we can construct a loss function where we have n terms per realization. In each of these terms, we are fitting each of these entries of the output vector to the target, right? So we are learning at the same time, we are fitting all these outputs at the same time, and therefore learning to predict the or estimate the map given any number of measurements. So let me show some numerical results. We will be comparing the proposed estimator with just 100,000 parameters with traditional and deep learning estimators. Deep learning estimators have more or significantly more parameters than the proposed algorithm. So in these figures, we see that the proposed algorithm outperforms all existing estimators, and this is not surprising. Traditional estimators cannot learn from data, whereas deep learning estimators require grid discretization. So the proposed algorithm does not need grid discretization and can learn from data, and this is why it attains the best results. So now I will briefly touch upon the second contribution of this paper, which is active sensing for radio map estimation. In this problem, we are also given a set of measurements, but we are also given m candidate locations. The problem is to choose the candidate location such that measuring there is most helpful to estimate the map, right? So it's kind of the most informative location, right? And this is of great importance for network operators in cellular systems. So to solve this problem, what we do is to extend the transformer that we have for radio map estimation with another transformer that operates in parallel and that takes as input the features of the candidate locations. This second transformer returns a vector whose length is precisely the number of candidate locations. The mth entry here quantifies the quality of the mth candidate location for estimating the map, right? So choosing the best candidate location is just a matter of finding the largest number in this vector. And to train this transformer, what we do is to give the estimation transformer both the candidate locations as well as the measurements at the candidate locations which are available at training time. And then we design a loss function where the elements of this vector are as regarded as attention coefficients over these estimates here. So I don't really want to spend time here. The details can be found in the paper. And experimental results reveal that this approach is quite promising. We see that the error that we get with this scheme is significantly lower than the error that we would get by just choosing a candidate location uniformly at random. All right, so it remains only to explain how we applied these ideas in the real world. In particular, we developed and deployed an app for radio map estimation using smartphones, where the smartphones collect measurements and show the maps to the user. The idea is that the measurements are sent to the server, which estimates the maps and send them back to the smartphone. And among the estimators that we implemented, we included the transformer estimator that I described earlier today. And among the metrics that are mapped, we have these ones here, which characterize pretty well the quality of a connection in these cellular technologies here. When it comes to platforms, this app has been developed for Android and is currently in the testing phase. For downloading it, please visit this URL here. It's not possible to develop such an app for iOS as far as we know, because of limitations of Apple devices, which do not provide the kind of information that is necessary to collect measurements. And it is important to note here that a large number of challenges arise when implementing estimators like this in the real world. As we know, in theory and practice are the same, but in practice they are not, right? So among the challenges that we encounter, we have that Earth is round, and therefore we need to project the surface onto plane regions, and that all gives, of course, some headaches, right? We can use the so-called Mercator system, which is used by Google Maps and other systems, but still is problematic, right? We need to divide the world into tiles for estimation, and we need to ensure that these tiles have similar size to use the same parameters for all for each estimator, right? And that means that we need to define zoom regions based on latitude, and that makes the communication a bit cumbersome. Then there are also challenges when it comes to computation. We need to be able to generate maps or construct radar maps pretty quickly, and that means that we need to use multi-threading, and we need to optimize the code significantly. Race conditions arise also because of the usage of the GPU, which also leads to memory issues and so on. There are also issues with the database. One needs to minimize the number of queries and things like that. There are all additional issues, additional challenges with storage, security, privacy, and so on. So one, of course, needs to expect quite a significant amount of time for developing a system of this kind. So this is the app. It comprises 4 views. The first 2 can be used to collect measurements. One can adjust how frequent the measurements are, both in space and time. And this runs can be run in the background, so that the app can be closed and it keeps collecting data. So this is now the view to show estimated maps, right? So we can choose the technology, filter by operators, we can choose the metric, and here we selected the transformer based estimator that I described earlier. So the estimates, the map estimates, are requested to the server, and one can zoom in and out, and then the corresponding zoom levels will be rendered in the backend, right? Because depending on the zoom level, we need to adopt a certain resolution in the when generating the map. Finally, I would like to thank our development team, as well as our sponsors. Without them, this wouldn't have been possible. And I would like to wrap up. We looked at attention from a general perspective, beyond the standpoint of large language models. We found that attention mechanisms can be applied in a broader family of problems that share some formal features in common. We apply these ideas to develop a radio map estimator and to solve the active sensing problem. Finally, we looked at how we developed and deployed an Android app that implements these ideas in the real world. As future work, we need certainly more experimental studies and to address some of the limitations of these schemes, such as, for instance, the need for accommodating side information for radio map estimation. And this brings us to an end. I thank you very much for your attention, and I'll see you next time.